Okay, welcome to the second unit. On this unit we are going to see how to solve differential equations of higher order. But still those differential equations will be linear differential equations. What does that mean? Well, it means that the y and the derivatives of y are, the power is 1, okay? Now, we have already seen linear differential equations in the first unit. If you remember, this is the linear shape of the differential equation. And something I said on the videos is that the linear differential equations are composed of two things. The general solution is composed by one part, what is the homogeneous solution, and that homogeneous solution is the differential equation when it is equal to 0. Now, that homogeneous solution always have a constant. And then plus a particular solution. This particular solution is the solution when it is not equal to 0, when it is equal to q of x. Okay, now, what we are going to do in the second unit is to expand this differential equation into higher order. Let me give you one example of the higher order. So it's going to be, for example, second derivative of y with respect to x squared plus p of x, derivative of y with respect to x plus, this is new, r of x, y equal to q of x. So as you can see, here is the same differential equation, but this is second order differential equation. Okay, now, keep in mind this, that you have the first coefficient is equal to 1. Okay, that is going to be helpful when we develop the formulas. Okay, so how is the solution? Well, the solution is very similar. As you can see here, this is linear differential equation because the power of y is 1, the power of this derivative is 1, and the power of this is 1. Now, pay attention that the order, the number of derivatives, and the power, they are different. One is the degree, and the other is the order of the differential equation. Okay, so all of them has power 1, so this is still linear differential equation. Now, the general solution is going to be very similar. The general solution is going to be C1 y1 plus C2 y2 homogeneous solution. This part is still the homogeneous solution. Plus the particular solution. Now, as you can see here, we have a bigger homogeneous solution. You can see here we have one solution and the second solution. So what we have to do in this unit is to find those two solutions. And the first unit, it was only one solution of the homogeneous. Now the reason of what you have only one solution is because here the degree is first order differential equation. So you will have only one solution in the homogeneous. In this case, it is second order differential equation. That means that the homogeneous solution is going to be composed by two solutions, y1 and the y2, and each one of them is going to have their own constant, c1 and the c2, plus the particular solution. Again, so this part is when it is equal to 0. When it is equal to 0, that is the homogeneous solution, alright? Okay, so we are going to try to solve this differential equation, but the differential equation could be higher in order. So if we increase this in another number, and the next order, the next derivative is going to be the third derivative of y with respect to x squared to the power of 3 plus p of x, and now this one is going to be second derivative with respect to x plus r of x first derivative plus s of x, I'm going to write s of x, y equal to q of x. Okay, so this is third order differential equation, so the solution is going to be something like this. The solution, the general solution is going to be c1 y1 plus c2 y2 plus c3 y3 plus the particular solution. And again, here you have your homogeneous solution. Homogeneous solution. As you can see here, you have three solutions, y1, y2, and y3. And that is because you have third order differential equation. So this is the rule. The order of the differential equation is the number of solution in the homogeneous part. Okay, because you have third order, then you have three solutions, and you will have three constants. All right. Now, the particular solution is just still the same, and the particular solution is related to the Q of x. This part in green is just when this is equal to 0. All right. As you can see here, the coefficients are variable except for the first one, which we expect to be 1. But you know the fix to that. If this is not equal to 1, all you have to do is to divide by the value here, whatever you have here, as long as it is function of x, and then you will have the shape of the differential equation. Alright, now what we have to do here is we are going to start with, let's assume for the moment, to make this problem easier, let's assume that the differential equation is homogeneous. Let's deal with the homogeneous part first. First, deal with finding the homogeneous solution. So that means that Q of x is equal to 0. So the differential equation that we are going to deal is with this one. Second derivative of y respect to x squared plus p of x first derivative respect to x plus r of x, sorry, r of x times y equal to 0. So because this is homogeneous, we are going to find the general solution will be only, the general solution is going to be just c1 y1 plus c2 y2. So we don't have to calculate the particular solution. So that makes it easier for us to find this kind of solution. We are going to just find the homogeneous solution now. In later, we are going to find the particular solution later. Okay, to make this even easier, let's assume constant coefficients. Right? So that what does that mean? Well, p of x is not a function of x, and the r of x is not a function of x. They happen to be constants. Okay, so I'm going to write it like this. Second derivative of y respect to x squared plus some value p derivative of y respect to x plus r y equal to 0. So they are no longer function of x, could be 5, 10, minus 3, whatever, right? So this one is going to be easier to solve because you have to, but still you have to find two solutions, and we are going to start with a second order differential equation, all right? Okay, I'm going to transform this into this kind of differential equations. A second derivative plus b first derivative plus c y equal to 0. I just replace the second derivative with double prime and the first derivative with the one prime, which is another way to write the differential equations. And I have replaced it here the constant. So the first one is going to be a, the second coefficient will be b, and the third coefficient will be c. Now this is very similar to the chicharronera. If you remember the chicharronera, ax squared plus bx plus c equal to 0. And the solution of the chicharronera, I'm sure you remember, x1 and 2 is going to be minus b plus minus the square root of b squared minus 4ac over 2a. So that is the solution of the polynomial equation of second degree. Now, I write it the same order a, b, and c because there's some relation on that. We are going to solve the differential equations just like this one, okay? So, engineers, we are going to solve this kind of differential equations, but we are going to start with the easiest, which is just a higher order of the linear differential equation, second order, with equal to 0. That means that you don't have to worry about the particular solution. All you have to worry is the homogeneous solution, and we are going to make the coefficients constant. All right? So we are going to start by solving how to solve this differential equation. So this is the start. All right? In the next video, we are going to see how to solve it.